The earwig's delicate, paper-thin wings can open 10x their folded size due to its origami-like creases. Credit ETH Zurich, Purdue University. Article by Rohini Subrahmanyam, originally published by Knowable Magazine as the microscopic, tear-shaped Lacrymaria. Olor swims around hunting for food. It does something remarkable. In a blink, the tiny protist extends its neck more than 30 times its body length, snatching up unwitting prey.
Then, just as quickly, the neck withdraws, returning to its original size. The movement is akin to a 6-foot human suddenly stretching their neck some 200 feet and then snapping it back to normal. This acrobatic behavior had been observed for more than 100 years, yet only in 2024 did scientists finally understand how olor manages to whip out and store its neck so deftly. The tiny hunter uses a kind of cellular origami. It folds its external membrane in pleats that it can unfold, deploy, and retract at will. This particular origami, which we named Lacrymaria, humans did not invent it, nature invented it, says Stanford University bioengineer Manu Prakash. Like releasing tightly spooled fishing line, the tiny, single-celled hunter Lacrymaria olor can rapidly extend its neck 30 times its body size and just as quickly whip it back into itself. Anyone who has dabbled in origami knows that it can be frustratingly complicated, yet somehow its intricate folds have arisen naturally many times in living things. In recent years, scientists have taken a closer look at these complex folds of the biological realm, such as in delicate insect wings, a chick's developing gut, or the lightning-fast neck of olor. Some of what they are finding is inspiring practical applications, such as drones and robots, but the nature of origami itself is enough to keep scientists fascinated. Origami exists at a particular boundary, says Harvard University physicist Lacrymaria, where there is just enough balance between constraints and freedom so that you can do remarkable things. Frontiers in space. Japanese people started practicing origami sometime around the 6th century, but it wasn't until about 40 years ago that scientists and engineers began investigating origami in earnest. Early studies focused on usefulness in space. With origami, one could tightly pack solar panel arrays on a rocket for unfolding later on. Japanese astrophysicist Koryo Miura published what became a standard folding technique for such applications in 1935. Called the Miura, this rigid fold is made of mountain and valley creases. It's essentially a pattern of closely packed parallelograms. With one pull, you can unfurl an entire folded sheet, such as a map of an array of solar panels, and then just as easily fold it up again. In 1934, the fold was used to efficiently pack solar panel arrays in Japan's Space Flyer Unit satellite. Editor's note: this page is undergoing construction. Check back tomorrow if it seems like paragraphs are missing.
GMM team, the Miura fold or Miura has been used to compactly fold structures such as solar arrays that can then be unfolded in a single motion.
But long before then, the fold was deployed in nature. In a classic 2005 paper published in Science, Van and physicist Sergio Rica, currently at Pontificia Universidad Católica de Chile, posited that a Miura-like pattern could naturally occur in leaves or insect wings due to inherent physical instabilities. Using mathematical models and a drying slab of gelatin, they demonstrated how light compression on a stiff, thin skin that's supported by a soft, thick substrate can prompt the skin to settle into a Miura-like pattern, akin to how compression of the Earth's crustal plates can lead to mountains and valleys. More recently, Van and his team investigated how different parts of a chick gut, the large intestine with wrinkles, for example, the small intestine with zigzag folds, develop their very different creases. It turns out that the layers of gut tissue vary in thickness and stiffness across each portion. As the gut elongates during development, their mechanical properties cause these portions to buckle in different ways. The researchers reported in the Proceedings of the National Academy of Sciences in 2024. Other complex biological folds like the wrinkles on our brain are also likely to form during development due to similar physical force considerations. This is essentially a very natural consequence of pattern formation in physics, Van says. Insights from insect wing scientists are also investigating how insects neatly fold and unfold their wings. Andres Urrieta, a mechanical engineer at Purdue University, and Anders Studart, a materials science engineer at ETH Zurich, turned to earwigs, which have hindwings tucked away under their forewings. Just before flying, the earwig unfurls the hindwings and all the tightly packed creases elegantly open as thin, delicate wings stretching out to more than 10 times their folded size. The process takes place without the use of muscles. The researchers were drawn to the earwig wing for 3 reasons. It has a large change in area as it folds or unfolds. It's what scientists call bistable. It can be at rest in 2 different states, open and folded. And it doesn't just have standard straight origami creases, it has curved creases. Curved creases don't fold flatly along a straight line. They fold along a curve like a folded over shirt collar. They are trickier than a standard flat crease. As you fold along the curve, the crease changes direction ever so slightly at every point.
So at each point, the sheet needs to fold in two directions radially along the crease, where the two parts of the sheet bend like a hinge and come closer and tangentially to the crease.
Because the crease is curved, every part of it is angled slightly differently. It turns out that earwigs stretch their wings ever so slightly at the curved crease along the wing's middle.
It manages this stretching with an elastic protein called resilin that can store and release energy like a spring.
In the middle of the earwig, when a spot there,